Thermoacoustic power generation, electricity from sound and sand. Sound can absolutely generate electricity. This is not a metaphor, but a fundamental principle of physics. Oscillating pressure waves inside a sealed steel tube, driven by thermal energy stored in an $80 sand battery system, are capable of driving a magnet back and forth inside a copper coil. This electromechanical process generates alternating current, AC, which can be stored in batteries and used directly to power practical household appliances. From a technical standpoint, this is thermoacoustic power generation, a breakthrough successfully demonstrated at a practical scale by the Los Alamos National Laboratory in 1999. Their published research papers comprehensively proved the technical feasibility of this system. However, when weighed economically against maintaining long-term fuel sales versus a model where users build a one-time independent system, this technology was gradually pushed into the shadows. The system we will analyze in depth today requires a mere $80 to build. Notably, it operates entirely without internal combustion engines, turbines, solar panels, or wind turbine blades. Instead, the system stores heat in sand, then converts this heat into resonant pressure oscillations within a compressed gas column. Analytically speaking, these pressure oscillations are essentially sound waves. And they are used to directly drive a linear alternator. The result is a system that generates AC electricity with absolutely no rotating mechanical parts, offering an operational lifespan that could span decades. The engineering process shows that every assembly step is entirely feasible for the average user. All component parts can be easily purchased on the open market. Every piece of data presented here has a solid foundation and can be directly cross-referenced with peer-reviewed scientific literature. To decode the operating mechanism, we need to dive deep into thermoacoustics, one of the most elegant yet least publicly known branches of applied physics, core thermodynamic principles. The core thermodynamic principle here is very basic. When a gas is compressed, its temperature increases, and when it expands, it cools down. For a practical example, if you pump a bicycle tire vigorously, you can clearly feel the pump's cylinder warming up. Conversely, when you rapidly release pressure from a compressed gas canister, its metal casing immediately becomes freezing cold. The direct and tight proportional relationship between the pressure and temperature of a gas volume is the fundamental core of thermoacoustic physics. In this system, the pressurized gas is placed inside a sealed resonance tube, meticulously designed so that the reflecting pressure waves return perfectly in phase with the next emitted wave. This structure forms a sophisticated acoustic resonator, where the oscillation amplitudes are continuously and powerfully amplified. Based on the tight coupling between pressure and temperature, we can affirm that these pressure oscillations also occur in parallel with temperature oscillations. The crucial element is a porous regenerator fixed inside the tube, separating the hot and cold ends, acting as a transfer station for the gas masses to exchange heat during oscillation. Specifically, the gas absorbs heat as it moves toward the hot end and releases that heat on its return journey. This chain of reciprocating reactions forms a highly unique, self-sustaining physical cycle. In other words, the temperature difference is the agent that generates the oscillation, and conversely, that very oscillation maintains the temperature difference within the tube. As a result, the system can self-start from an initial temperature gradient to sustainably produce acoustic power. Historically, physicist Lord Rayleigh modeled this phenomenon using mathematical equations as early as 1887. It wasn't until 1999 that a brilliant research team at Los Alamos, led by Stephen Garrett and Scott Backhouse, succeeded in turning that theory into a working generator model. Their historic research, published in the prestigious scientific journal Nature, described a thermoacoustic Stirling engine connected to a linear alternator, which generated measurable electricity entirely without combustion or rotating parts. Recorded data showed they achieved a heat-to-acoustic energy conversion efficiency of 30%, a record high for thermoacoustic devices at the time. Subsequently, the linear alternator took over the conversion of this acoustic energy into actual electricity with an impressive efficiency of 80% to 90%. Calculated over the entire system, the total thermal-to-electric conversion efficiency reached a stable rate of 24% to 27%, the 6-stage energy conversion process. Moving on to the DIY experimental version we are analyzing. This system is constructed from common materials but accurately replicates that complex energy conversion chain at an incredibly accessible cost. Naturally, the efficiency of this DIY version will be lower than the Los Alamos Laboratory configuration, but the core physical principles governing them are completely identical. We can break this generation system down into an energy conversion chain comprising 6 specific stages. The general model is, heat is input at one end of the system, and useful electrical energy is extracted at the other, the sand battery chamber. Mechanically, it is a sealed steel drum filled with dry silica sand. This specialized sand mass is heated to a threshold of 150 to 300 degrees Celsius using heat sources like a wood stove, boiler, or solar thermal collectors. Acting as the heart of the model, this central thermal energy storage provides the driving force for the system. Material-wise, sand has a high thermal mass, allowing it to maintain this temperature for hours and linearly, stably release energy into the adjacent hot heat exchanger. The hot heat exchanger, its structure consists of a coiled copper tube pressed tightly against the wall of the sand battery drum, containing the working gas maintained under compressed pressure. As the gas moves through this contact zone, it aggressively absorbs heat from the drum's surface and exits with soaring temperature and pressure parameters. The regenerator, this is a special cylinder made from porous heat-dissipating materials, such as stainless steel mesh or ceramic foam. Positionally, this component is fixed inside the resonance tube, serving as a strategic barrier between the hot and cold heat exchangers. As the oscillating gas flows back and forth through this filter, it exchanges heat with the porous structure in each direction of movement, creating an optimal acoustic oscillation amplification mechanism. The cold heat exchanger, designed to handle excess heat, this is a second copper coil installed on the cold side of the regenerator, directly exposed to the ambient air. Its critical technical task is to extract excess heat from the returning gas, thereby preserving the temperature differential, the core driving factor dictating the system's operation. Without this cooling mechanism, the thermal gradient would immediately collapse, leading to the complete nullification of oscillation amplitudes. The linear alternator, mechanical energy begins its conversion here. This electromechanical component consists of a piston assembly connected directly to a magnet core, performing reciprocating linear motion inside a copper coil, driven by the continuous thrust cycle of the pressure waves. Electromagnetically, each stroke of the piston sweeps through the magnetic field and generates exactly one half cycle of alternating voltage. This raw AC power is then passed through a rectifier to be converted into direct current, DC, for battery charging or direct power supply. The power output module, this provides useful commercial electricity for lighting systems, charging telecommunications equipment, or replenishing energy storage batteries. In summary, this is a continuous, closed-loop conversion chain. Heat from the sand battery generates sound waves, which transfer kinetic energy to the linear alternator, and ultimately converge into useful electrical current on the circuit board. DIY construction guide specifications. To materialize this project, we must analyze the bill of materials, strict technical specifications, and practical market reference prices. The sand battery, the structural foundation, is an unlined 55-gallon steel drum, typically priced between $8 and $14 at agricultural supply stores or scrapyards. Notably, if you already have a 2-drum sand battery system, integrating this thermoacoustic engine in parallel is entirely technically feasible. Working gas, helium is rated as the superior medium because the speed of sound in it is nearly 3 times higher than in regular air. Acoustic analysis shows a helium environment allows a standard resonance tube to achieve a frequency of approximately 536 Hz, meaning denser oscillation cycles per second and directly yielding higher electrical output. Resonance tube preparation. The inner surface of the steel resonance tube must be thoroughly cleaned with a mechanical wire brush, then sterilized with acetone or industrial alcohol. Any residual rust, oil sludge, or dust particles will severely degrade the regenerator's efficiency by clogging the porous structure and causing parasitic thermal short circuits. The tube must be perfectly clean bare steel before installation. Regenerator fabrication. The optimal method is to cut heat-resistant mesh sheets into strips 190 mm wide, then tightly roll each strip into a solid cylinder. Coaxially stack 6 to 8 of these mesh cylinders in series inside the steel tube. Filling a volume spanning 80 to 100 mm exactly at the tube's center coordinate. You must use a wooden dowel to apply even pressure, maximizing the contact area between the outer ring of the mesh and the inner tube wall. The regenerator must be compressed tightly enough to resist mechanical shifting forces, but not beyond the limit that causes deformation and eliminates the void spaces between the mesh layers. Spatial positioning: the regenerator must be anchored exactly midway along the tube's length, isolating roughly 400 to 450 mm from each end. The hot heat exchanger port is set at the 0 mm coordinate, while the opposite area integrating the cooling assembly and linear alternator occupies the 900 mm mark. This symmetrical arrangement optimizes the sound wave transmission path length, allowing the pressure wave space to self-amplify before hitting the end caps. Hot heat exchanger assembly: sequentially wind 15 to 18 turns of 6 mm copper tubing tightly around a master core mandrel. The coils must have high tightness, nearly touching each other to maximize the heat exchange surface area. Prior to bending, the copper tubing must be annealed using a propane torch, heated to a dull red glow, then air-cooled, to prevent structural cracking. After forming, braze or solder the inlet and outlet sections to pre-threaded fittings on the hot end cap. The entire outer surface of the coil must be pressed forcefully against the outer wall of the sand battery drum and securely locked with stainless steel hose clamps. Sealing: for pressure safety, high-temperature silicone sealant must be used on all threaded joints before assembly, followed by hand tightening plus exactly one full mechanical turn. The system constantly operates at 2 to 3 atmospheres, so absolute sealing is mandatory. Cold heat exchanger: wind 8 to 10 sequential turns of copper tubing around the cold end of the resonance tube, leaving the two ends exposed to ambient air. Natural convective air cooling is generally sufficient, but adding a $2 small cooling fan to force air over the coil is a smart upgrade to widen the temperature differential. Linear alternator: you can build the system's electromagnetic heart from recycled audio speaker parts. A traditional dynamic speaker is fundamentally a linear electromagnetic transducer. By operating it in reverse, forcibly applying mechanical oscillations to the voice coil, you directly extract electrical energy, complying with Faraday's law of electromagnetic induction. Carefully disassemble an old subwoofer, keeping the magnetic field assembly and voice coil former intact. Remove all unnecessary acoustic parts, paper cone, rubber surround, dust cap. Mount the magnet unit to the cold end cap using an aluminum bracket, perfectly aligning the voice coil former coaxially with the piston connecting rod. Fabricate a lightweight aluminum piston disc, 45 to 48 mm diameter, with a pre-machined threaded center shaft. Thread the rod through a linear guide bearing system and securely attach the voice coil former. Electrical circuitry: wire the voice coil output to a bridge rectifier board, for diodes, $1, to convert raw AC to pulsed DC. Route this current through a smoothing capacitor before connecting it to a battery charging board. Operating in helium at 2 atmospheres, a well-assembled prototype will produce an open-circuit DC voltage of 2 to 8 volts, perfect for charging 18,650 lithium batteries or powering LEDs. Operation and power output analysis: the process of heating the sand battery and the initial startup cycle are extremely critical. Connect the heat source to the drum's intake port and maintain continuous combustion for about 2 hours. The goal is to push the drum's surface temperature at the heat exchanger contact zone to a minimum operating threshold of 150 to 200 degrees Celsius. If the heat is below 120 degrees Celsius, the differential will not create enough potential energy to trigger spontaneous oscillation in air. However, using helium at 2 atmospheres drops the critical startup threshold to just 90 to 100 degrees Celsius. Once the drum's surface passes 150 degrees Celsius, begin pressurizing the resonance tube system with helium. Pump the gas in increments of 0.5 atmospheres, pausing for 2 minutes to stabilize between cycles. When the parameters align, the system will automatically initiate acoustic oscillation. You will hear a low-frequency tone emitting from the resonance tube before the gauges even register it. This ultra-low frequency sound is the acoustic power being actively converted into electricity. Connect a multimeter to the rectifier output immediately. The voltage initially hovers between 1 and 2 volts, rising linearly over 15 to 20 minutes as the system reaches thermal equilibrium. Once stable, record the open circuit voltage, connect a small resistive load, like an LED strip or 5 ohm resistor, and observe the loaded voltage. The difference provides the basis for calculating source impedance and true power output. Power output, evaluated on a standard configuration, 900 mm tube, 55-gallon sand battery at 200 degrees Celsius, 2 atmospheres of helium, recycled speaker alternator. This system produces a continuous steady-state output of 0.5 to 3 W. While this is not 30 W or 300 W, from a macro energy perspective, it is immense over a full thermal charging cycle. A fully charged sand battery can provide 8 to 12 hours of continuous power. Maintaining 2 W for 10 hours yields 20 Wh, enough to charge 3 18,650 batteries, light up an area all night, or maintain radio/GPS communications. Scalability: doubling the resonance tube's diameter increases available acoustic power approximately threefold. Running two 100 mm tubes in parallel on the same heat source is projected to yield 3 to 10 W, enough to trickle charge a 12V lead-acid battery and potentially run a small inverter. Conclusion: economic context and true value. Objectively, this thermoacoustic technology was not born to replace solar panels in raw current output. Its true technological value is the ability to convert heat into electricity at night, indoors, when the wind is still, and the sky is heavily overcast. Furthermore, it runs on an energy source, firewood, you can gather yourself and safely store in sand. It thrives in the harshest conditions where traditional renewables fail. For an $80 investment, you get a system with a very clear conversion cycle: heat in, electricity out via sound waves. This perfectly aligns with Los Alamos Laboratory's 1999 peer-reviewed findings. The core strength is the complete elimination of direct combustion. Rotating shafts, turbine blades, oil changes, and spark plugs. The only maintenance is periodically repressurizing the gas if it diffuses through the seals over many months. In the early 2000s, the global energy industry evaluated this. Their concern wasn't whether the physics worked, that was completely transparent. The core issue was whether a technology producing electricity from stored heat, immune to fuel costs, lacking moving parts, and buildable for $80, could coexist with a business model built on monthly utility bills and exclusive maintenance contracts.